A spacecraft has flown into the atmosphere of the Sun, passed through plasma burning at roughly 2 million degrees Fahrenheit, and come back out, still working. The nearer it drew, the more it kept measuring things that no existing theory of the Sun can account for, beginning with a single impossible fact: the Sun's atmosphere is nearly 200 times hotter than the surface lying beneath it. Think for a moment about how strange that is. The visible surface of the Sun, the layer that sends us our light and our warmth, sits at around 10,000 degrees Fahrenheit. Move outward into the thin outer atmosphere we call the corona, away from the heat source, and the temperature does not fall. It climbs to about 2 million degrees. Every instinct you have about heat says this cannot happen. A cup of coffee does not grow hotter the farther your hand drifts from it. Yet the corona does exactly that, and physicists have known about the contradiction since the 1940s. NASA calls it one of the greatest unanswered questions in all of astrophysics, and 80 years of theory has not closed it. To learn what heats that outer atmosphere, you cannot simply watch from a distance. You have to go there, into the fire, and take the measurement in place. I'm Dr. Bernhard Kessler, and this is the kind of story I make this channel for. If you want more of them, take a second to subscribe. Everything you are about to hear comes from published research and named scientists rather than from hype. The Sun is strange enough without it. To understand why a spacecraft was sent into that fire, go back to a young physicist named Eugene Parker. In 1958, Parker wrote a paper arguing something almost nobody believed: that the Sun does not sit quietly in space, but constantly blows a stream of charged particles outward in every direction, fast enough to turn supersonic. He called it the solar wind. He submitted the work to the Astrophysical Journal, and 2 referees moved to reject it. What makes the episode remarkable is that neither reviewer pointed to an actual mistake. They simply did not accept the conclusion. Under normal circumstances, that would have ended it. But the journal's editor was Subramanian Chandrasekhar, and Chandrasekhar read the mathematics himself, found no flaw in it, and overruled both referees. The paper was published. Chandrasekhar would later share the 1983 Nobel Prize in Physics, and NASA would name an entire flagship observatory, the Chandra X-ray Observatory, in his honor. The man who refused to silence Parker was not a minor figure. For years, the solar wind stayed an idea on paper, defended by one editor and doubted by much of the field. What finally settled the argument was not a better calculation, but a spacecraft. In 1962, NASA's Mariner 2 traveled toward Venus carrying an instrument that could sample the particles around it, and 2 researchers at the Jet Propulsion Laboratory, Marcia Neugebauer and Conway Snyder, read the data. They found a continuous supersonic wind of particles streaming from the Sun, present the whole way, exactly the flow Parker had described 4 years earlier. The prediction 2 referees had tried to throw out was simply, measurably true. That is the arc worth holding on to as the rest of this unfolds, an idea dismissed, defended by a single editor, and confirmed at last by going out into space and touching the thing itself. Decades later, NASA did something it had never done. When it built a probe to fly closer to the Sun than anything before it, the agency named the spacecraft for Eugene Parker while he was still alive, the first time it had ever named a mission after a living person. And it added a quiet, fitting touch. Engineers bolted a copy of that rejected 1958 paper to the spacecraft, along with a memory card carrying more than 1 million public names, and sent the once-doubted theory back toward the star it described. In August of 2018, at Cape Canaveral, Eugene Parker sat and watched a Delta IV heavy rocket carry his name off the Earth, the first person ever to see a mission named for himself leave the planet. The probe that departed that morning would become the fastest object human beings have ever built, reaching 430,000 miles per hour as it grazes the sun. The vindication was no longer an argument in a journal. It was a machine, moving faster than anything we have made, carrying his paper into the corona. When Parker's solar probe finally reached in close, the sun it found was not the tidy one in the textbooks. The corona had always been drawn as a smooth, glowing halo. Up close, it was nothing of the kind. The first results, published in the journal Nature in December of 2019, described a corona that was chaotic and densely structured, its outer boundary warped and shifting rather than clean. Running through it was something stranger still. The sun's magnetic field was folding back on itself in sharp, S-shaped reversals, kinks where the field briefly flips direction and snaps back. Researchers named them switchbacks. The probe was flying through far more of them than any model had predicted. The theory Parker had staked his career on was confirmed in its broad strokes, and yet the closer the spacecraft looked, the more new questions it raised about how that outer atmosphere actually behaves. To feel what this probe truly does, follow it through a single close pass. On the 28th of April, 2021, Parker's solar probe became the first spacecraft in history to fly inside the sun's atmosphere. It crossed a boundary called the Alphean critical surface, the line below which the sun's magnetic field is strong enough to hold the plasma to the star rather than let it escape as wind. For about 5 hours it flew beneath that surface, inside the corona itself, before climbing back out. During its closest approaches, the probe travels alone and out of contact with Earth for days at a time. The front of its heat shield reaches around 1700 degrees Fahrenheit, while the instruments a few feet behind it stay near room temperature. Engineers cannot place a thermometer on the face of that shield, so they judge its health by how steady the temperature holds. A slow drift upward would mean heat was leaking through, that the shield had begun to crack. As long as the number stays flat, the spacecraft is alive. Then, the probe began to unmake the very picture it had helped build. If switchbacks were born at the sun's surface, they should be most common deep in the corona and thin out farther away. Parker found the opposite. Inside the corona itself, the switchbacks vanished. Analysis led by Mojtaba Akavan-Tafti at the University of Michigan, published in 2024, concluded that the reversals cannot be forming at the surface at all, they must be generated later, out in the solar wind. The instrument built to confirm the solar wind was now overturning the explanation for its own strangest feature. Then came an explosion. As Parker crossed a magnetic boundary near the sun, it watched a burst of particles fling protons and heavier ions in completely different patterns, the protons spraying outward like the beam of a flashlight, the heavy ions shooting out in a tight straight line like a laser. Work led by Mihir Desai at the Southwest Research Institute reported this in 2026, and the standard theory of magnetic reconnection says both kinds of particle should be accelerated the same way. They were not. None of this stays safely out at the sun. The same wind, flares, and eruptions Parker flies through are what reach the Earth, threatening satellites, power grids, and aviation, along with the astronauts NASA intends to send to the Moon and eventually Mars. Parker sits inside that weather before it arrives. In September of 2022, the probe flew directly through one of the most powerful coronal mass ejections ever recorded, a full solar explosion from less than 6 million miles above the surface. It survived, and its cameras caught the eruption doing something no one had watched before, sweeping interplanetary dust outward ahead of it like a vacuum cleaner, clearing a path millions of miles long. That is a storm measured from the inside, at the place where any warning to Earth would have to begin. And after all of it, the oldest question is still open. 80 years on, no one has settled why the corona is so much hotter than the surface below it. In July of 2026, researchers led from the University of Alabama in Huntsville proposed a factor no equation had ever included: tiny charged grains of dust near the sun that may help decide how the corona heats. Parker has already made the closest pass it will ever make. A final flyby of Venus locked it into an orbit it can never tighten again. One day its fuel will run out, its body will turn and burn away in seconds, and only the bare carbon heat shield will remain, still carrying that rejected paper and over 1 million names, circling the sun for perhaps 1 billion years. So the probe flew into the atmosphere of the sun, and what it detected was not an answer, but a deeper mystery. A star still heating its own outer air by a mechanism we cannot name. If there is a question you want covered next, leave it in the comments, and a like genuinely helps this reach other people who wonder about the same things. Subscribe, and I'll take you back to the sun.